A boost converter is a DC to DC power converter with an output voltage greater than its input voltage. It is a class of switched-mode power supply containing at least two semiconductors and at least one energy storage element, a capacitor, inductor, or the two in combination. Filters made of capacitors are normally added to the output of the converter to reduce output voltage ripple. Overview. Power for the boost converter can come from any suitable DC sources, such as batteries, solar panels, rectifiers and DC generators. A process that changes one DC voltage to a different DC voltage is called DC to DC conversion. A boost converter is a DC to DC converter with an output voltage greater than the source voltage. A boost converter is sometimes called a step-up converter since it steps up the source voltage. Since power and lighting systems, the NHW20 model Toyota Prius HEV uses a 500V motor. Without a boost converter, the Prius would need nearly 417 cells to power the motor. However, a Prius actually uses only 168 cells and boosts the battery voltage from 202V to 500V. Boost converters also power devices at smaller scale applications, such as portable lighting systems. A white LED typically requires 3.3V to emit light, and a boost converter can step up the voltage from a single 1.5V alkaline cell to power the lamp. Boost converters can also produce higher voltages to operate cold cathode fluorescent tubes in devices such as LCD backlights and some flashlights. An unregulated boost converter is used as the voltage increase mechanism in the circuit known as the dual thief. This circuit topology is used with low-power battery applications, and is aimed at the ability of a boost converter to steal the remaining energy in a battery. This energy would otherwise be wasted since the low voltage of a nearly depleted battery makes it unusable for a normal load. This energy would otherwise remain untapped because many applications do not allow enough current to flow through a load when voltage decreases. This voltage decrease occurs as batteries become depleted, and is a characteristic of the ubiquitous alkaline battery. Since the equation for power is when the switch is closed, electrons flow through the inductor in clockwise direction and the inductor stores some energy by generating a magnetic field. Polarity of the left side of the inductor is positive. When the switch is opened, current will be reduced as the impedance is higher. The magnetic field previously created will be destroyed to maintain the current towards the load. Thus the polarity will be reversed. As a result, two sources will be in series, causing a higher voltage to charge the capacitor through the diode D. If the switch is cycled fast enough, the inductor will not discharge fully in between charging stages, and the load will always see a voltage greater than that of the input source alone when the switch is opened. Also, while the switch is opened, the capacitor in parallel with the load is charged to this combined voltage. When the switch is then closed and the right-hand side is shorted out from the left-hand side, the capacitor is therefore able to provide the voltage and energy to the load. During this time, the blocking diode prevents the capacitor from discharging through the switch. The switch must of course be opened again fast enough to prevent the capacitor from discharging too much. The basic principle of a boost converter consists of two distinct states. In the on state, the switch S is closed, resulting in an increase in the inductor current. In the off state, the switch is open and the only path offered to inductor current is through the flyback diode D, the capacitor C and the load R. This results in transferring the energy accumulated during the on state into the capacitor. The input current is the same as the inductor current as can be seen in Figure 2. So it is not discontinuous as in the buck converter, and the requirements on the input filter are relaxed compared to a buck converter. Continuous mode. When a boost converter operates in continuous mode, the current through the inductor operating in steady conditions During the on state, the switch S is closed, which makes the input voltage flowing through the inductor during a time period by the formula. At the end of the on state, the increase of Il is therefore D is the duty cycle. It represents the fraction of the commutation period T during which the switch is on. Therefore D ranges between 0 and 1. During the off state, the switch S is open, so the inductor current flows through the load. If we consider 0 voltage drop in the diode, and a capacitor large enough for its voltage to remain constant, the evolution of Il is. Therefore, the variation of Il during the off period is. As we consider that the converter operates in steady-state conditions, the amount of energy stored in each of its components has to be the same at the beginning and at the end of a commutation cycle. In particular, the energy stored in the inductor is given by, so, the inductor current has to be the same at the start and end of the commutation cycle. This means the overall change in the current is zero. Substituting in by their expressions yields. This can be written as the above equation shows that the output voltage is always higher than the input voltage, and that it increases with D, theoretically to infinity as D approaches 1. This is why this converter is sometimes referred to as a step-up converter. Rearranging the equation reveals the duty cycle to be discontinuous mode if the ripple amplitude of the current is too high. The inductor may be completely discharged before the end of a whole commutation cycle. This commonly occurs under light loads. In this case, the current through the inductor falls to zero during part of the period. Although slight, the difference has a strong effect on the output voltage equation. It can be calculated as follows. As the inductor current at the beginning of the cycle is zero, its maximum value is during the off period. Il falls to zero after. Using the two previous equations, delta is the load current I/O is equal to the average diode current. As can be seen on Figure 4, the diode current is equal to the inductor current during the off state. Therefore the output current can be written as replacing Il max and delta by their respective expressions yields. Therefore, the output voltage gain can be written as follows. Compared to the expression of the output voltage gain for continuous mode, this expression is much more complicated. Furthermore, in discontinuous operation, the output voltage gain not only depends on the duty cycle, but also on the inductor value, the input voltage, the commutation period and the output current.